Hi, my name is Evan. Today I'll be talking about the exploration problem in meta-reinforcement learning. This is joint work with my fantastic collaborators, Aditi, Percy, and Chelsea. Broadly, our goal is to learn agents that can adapt quickly to new but similar tasks from very few interactions. This is preferable to learning a separate agent for each task, as that can be extremely sample inefficient. As a motivating example, we'll consider learning a robot chef. The robot chef is allowed to train on many different kitchens during meta training, and then must cook in a new kitchen during meta testing. In the typical setting, we allow the robot chef to first spend one episode exploring around in the new kitchen, gathering whatever information it needs, before performing the execution episode, where it actually needs to cook a meal and maximize rewards. In this work, we focus on how to spend the exploration episode. Some forms of the exploration are really useful. For example, investigating the drawers to find ingredients needed later to cook a meal during execution. Other forms of exploration are not very helpful, such as admiring the decorations on the walls. A common approach for this exploration problem is to directly optimize exploration and execution behaviors end-to-end to maximize reward. However, this introduces a chicken and egg problem, where learning good execution behaviors requires already having learned good exploration and vice versa. More concretely, at the beginning of training, both exploration and execution are typically bad due to random initialization. If exploration is bad and the robot chef does not find the ingredients, then learning good execution behaviors, such as cooking, is really challenging, since it doesn't even know where the ingredients are. On the other hand, if the robot chef has bad execution behaviors and does not know how to cook, then no matter what it does during exploration, it will still not successfully cook a meal. Therefore, it will always achieve low reward, and learning the exploration behaviors will be extremely challenging. The key idea behind our approach, which we call DREAM, is to avoid this chicken and egg coupling problem by learning exploration and execution behaviors independently from each other. From a high level, DREAM consists of two main steps. First, we learn an execution policy independently from the exploration policy and learn to identify key information required for execution. Then, once we've identified what information is necessary for execution, we learn an exploration policy to recover that information. More concretely, in the first step, we assume access to a problem identifier during meta training but not meta testing. In this example, the problem identifier encodes different attributes of each kitchen, such as wall color, ingredient locations, and decorations, but in other scenarios could just be unique one-hots for each kitchen. Then, since the problem identifier encodes both information useful for execution, such as ingredient locations, as well as extraneous information, such as wall color, we apply an information bottleneck to the problem identifier and train an execution policy conditioned on this. Since the problem identifier encodes all the information necessary for execution, we can train the execution policy independently from exploration. Once we've learned a good bottleneck representation, which represents the information required by the execution policy, we can then train an exploration policy to recover this information. Concretely, the exploration policy produces different exploration episodes, and then we train the exploration policy based on a mutual information reward. Intuitively, this mutual information reward is high when the exploration episode is predictive of the bottleneck representation. In the kitchen example, where the bottleneck representation is the location of the ingredients, the reward is only high when the exploration episode looks through the drawers and finds the ingredients. Since the exploration policy is trained to produce trajectories that contain the same information as the bottleneck representation, which the execution policy uses, we can directly swap them out for each other during meta testing. We evaluate DREAM on a sparse reward 3D visual navigation task family, where each task is either to go to the key, block, or ball. Each object comes in two different colors, red or blue, and the agent must read the sign to figure out what colored object it should go to. The agent starts on the far side of the barrier and must walk around the barrier to read the sign. Here's an example of the exploration behavior learned by DREAM. The agent starts on the far side of the barrier and then walks around the barrier to read the sign. Once it's read the sign, it can then successfully perform tasks. In this case, the task is to go to the key, and since the sign says blue, it goes to the blue key. Quantitatively, we compare with existing state-of-the-art meta-reinforcement learning approaches. Of all approaches, DREAM is the only approach to actually read the sign, so it's the only approach to achieve reward and solve the task. Existing approaches either optimize reward end-to-end, which results in the chicken and egg coupling problem that we've described, or use different objectives for exploration, such as Thompson sampling. This avoids the coupling problem, but does not learn the optimal exploration policy. Thank you for your attention.